it's Mother's Day here too. But yeah, I really enjoyed the reading for this week. You mean Rizzy Condor, no? Yeah, no, I really enjoyed it. I enjoyed reading it, and I'm excited to see what you'll be talking about. So yeah. Yeah, I think we can get started. So, floor is yours.
we're basically like, we have a function on this, maybe very big, very complicated group, um, but we can get this orthonormal basis for the group by just representing it, with these irreducible representations, which is, just makes things computationally much easier and much simpler. And so that's kind of what we're going to be. These are like the kind of the core facts that we're going to try and be building up towards. So, but just kind of to like situate ourselves a little bit, I think kind of where we were at the end of last talk is that they're just, we have this idea that we want to represent a group with matrices, and it turns out that there are just a ton of ways to do this. So you can have like the trivial representation, and it's just like it maps everything to one, and then like the symmetric group, of permutations of three elements. All the symmetric groups also have another representation called the alternating representation that like it sends half of the elements to -1 and half to 1, and you can make a representation with that. And then there's like the obvious one that is the standard representation, and you just like permute the basis vectors. And so like 3, 2, 1, is that's just like you take the the 1, 0, 0 basis vector and you put it in the last place, and you put the last one in the first place, and you just get this. But so this is just like a simple group, and we've just found 3 different representations with different sizes, and like different sizes. And even if like this trivial and the alternating, like they're both one dimensional, but they're not the same. And I don't know, there's a lot of different ways to represent this group. And then it turns out that like if you have 2 representations, then you can combine them with like a direct sum. And so I don't know if you remember direct sums from linear algebra, but it's basically like you create a new matrix from 2 matrices with like by like block diagonal addition. And so this, you take, I can take my 2 one-dimensional representations, and I get a perfectly good 2-dimensional representation by just taking the direct sum. And so like, for that direct sum in the top left, it's always going to be 1. And then in the bottom right, it's going to be -1 for half and, +1 for the other half. But that's like a perfectly good representation, and you can also take the tensor product, which like, I don't know, there are lots of ways to talk about tensor products, and hopefully actually maybe we'll learn more about them soon. But like, you can also, you can represent it as a matrix where you basically do like the Kronecker product. But so like you can, that's another way to like take 2 representations and just put them together. And then also, honestly, like you can change the basis and just get a perfectly good representation. And so, and honestly, it's even crazier than that, because for every representation, you get a dual representation. Like you have this map. You have a map from G to to C, and you get a representation. And if you have 2 representations and you have a linear map between them, then there's a I don't know, like the point of this is that as soon as you start looking for representations, you start seeing them everywhere. and so actually I think maybe we should, so like what do we want to do? And what we really want is we want to be able to tell easily whether or not, if I have 2 representations, like, are they the same? And since it's so easy to take 2 representations and like just mash them together, if I have a representation, it would be really nice to find a way to like explicitly figure out what the sub-representations are. Like, okay, I've got this big representation. Can I break it up into smaller pieces? And it turns out, like, actually, yes, we can do this. And, in the way, like a lot of math, we do it by looking for an invariant. And a really good invariant for matrices is the trace, just, and which here we call the character. But most of the time I'm just going to write like tr, matrix. And, and it's the trace, and it's the sum of the diagonal elements. Does that all make sense? Any questions? And please, there are no dumb questions, so.
Sorry, can you go back one slide?
Yeah. Oh, I skipped ahead 2 slides, but this is the slide I was at before.
I think so. One thing I was wondering is like when you have this character, what is this with respect to? Like, is this for every given element in your group it has some character, or is this just a property, a singular value for that representation?
Okay, that is a very good question, and that is something that I should have that I probably should have set up front. And I think I was, so the character is a map from the group, like the group, and like an element of the group and the representation. It's like a map for that pair. And so, and it's a map from, yeah, I really should have said this explicitly. So it's a map from, specifically like one matrix, which is the representation of a single element of the group. And it's the trace for that element's representation. And so what we'll kind of see is, so kind of, what this means on the bottom here is that actually, because of the way the trace works, so the trace has this like cyclic property where, if you have three matrices and it's like A times B times C, or here this is rho H inverse, rho G, rho H, then you can cyclically permute them, and the trace doesn't change. And so because, rho H inverse, you can bring rho H inverse back from the end to the front, and then rho H inverse is just the identity. And so the trace has to be constant on what are called conjugacy classes. And so it only and conjugacy classes are like a way to partition up the group into you partition the group into a relatively small number of classes, and the trace is constant, and the characters are constant on those conjugacy classes. I honestly, I should have had a slide on conjugacy classes maybe, but I don't. Does that kind of make sense?
Yeah, totally. Thanks. I think that clears a lot of things up.
Yeah. So it's like, so the trace is a function on like a specific representation, and so sorry, is that another question?
Just wanted to comment that also because the trace is the sum of the eigenvalues of these matrices, it's also invariant up if you change the basis. So
yeah, yeah. So that's one thing that is really immediately great is if you have a representation, if you have 2 representations and the character agrees on all of the elements, or all of the conjugacy classes, which is the same, then you know that these are the same representation, and that there is just a change of basis that to like take you from one to the other. And then the other thing is that like I was talking before about how you can take direct sums, you can take tensor products to like take two representations and put them together. it's not as clean, well, right now, but we'll kind of get into this later. But the trace, like, if I have a big representation, then the trace gives me, like, clues, the characters give me clues about what the sub-representations can be, because, the sum, like, the sum of the trace is going to be the sum of all the sub-representations, right? And it's because, like, if I take the direct sum, like, the trace of the direct sum is the sum of the traces, and the trace of the tensor product is the product of the traces. Does that all kind of make sense of, like, why this would be useful? That, like, we get this, and then finally, the dimension of your representation is always going to be the character, the trace of the identity, and that's just because it's going to be ones along the diagonal, and so you get one per dimension. That all kind of makes sense. Okay, we can go back, and so I guess to kind of, I'm going to try and give, like, a really concrete example of being like, all right, I have this representation, and let's see if the trivial representation is a sub-representation. And so obviously, if it were just like the direct sum, like, and you didn't change the basis at all, and you were just kind of looking, you could just kind of look at it and be like, that one value on the diagonal is always one for every single group element, then that would be obvious. But, you really want to be, like, you might have this representation, and it's like, I don't know, the tensor product of a bunch of other representations, and, it is going to be in this weird basis. And so we want to just kind of check if the trivial representation is a sub-representation. And the way that we can do this is because it's like another way of saying that the trivial representation is a sub-representation, is we want to look for a subspace of our vector space that's totally closed under the action of rho. Like, for any, like, there's some subspace, like, and for, if the trivial representation is a sub-representation, anyway, like, there will be some subspace that, like, just does not change. It's totally invariant. And we can, and it turns out that actually there's, like, a pretty easy way to do this, and we just average, so we're looking for sub-representations of rho that are just like the trivial representation. And we can do this by literally just averaging rho. And so rho of G here is, a matrix, a n-dimensional matrix. And we just sum it, we just kind of get the average. And we get another matrix, and so that's going to be phi. And you can see that this, what we'll see is that now we have this average, and phi is totally invariant to phi takes a vector v and it projects it onto the invariant subspace. And you can see this by, like, if you take the action of any element of the group onto V, and you, like, see, like, phi of V, then, you, by linearity, you can bring, I guess I actually maybe have, oh, no, I do. Okay, so, phi is a matrix, and so you can kind of think of it as, like, phi is acting on the left from rho of h of v, and so that's why it's on the left. That's why it's on the right. And then by linearity, you can just kind of bring rho of h in there. And because this is a representation, rho of g times rho of h, which is like matrix multiplication, is the same as rho of gh. But the thing is, if you've got g, or you're summing over g, but then doing, like, the product of rho, of gh for all g, like, you aren't changing what you're summing at all. You're just kind of permuting the order of how you sum it. And so this is totally like, basically, phi of v is totally the same. No matter how, it's totally invariant to like the action of the group. Does this make sense? This kind of like set of steps? It's totally okay if it doesn't.
Maybe, I guess so. Like the reason is that any g in this sum you can express as like some other group element times h minus 1, so that's why it doesn't
Yeah.
change.
Yeah, no, that's precisely it. So
And then the reason, I mean, that's outside of the thing, but the reason like non-compact groups are evil is that you cannot take this average because like the 1 over number of elements doesn't really make sense for a non-compact group.
yeah, the way to extend this to um groups, like infinite groups in general, but in particular non-compact groups, is you need to be looking at so where I'm going to be kind of taking this is like, but basically you need to be looking at functions on the group that only have compact support. Um, and yeah, and so there are parts of that you can, so there are parts of all of this that you can extend, but there are parts where it just totally breaks. And even with like a compact but infinite group, I think like, yeah, in general, like you need to be careful. You need to be careful between, uh, uh, you know, yeah, like functions that are non-zero only for finitely many elements of the group, or ones that are have an infinite, but then hopefully, yeah, compact support. And yeah, anyway, but yeah, no, this gets a lot hairier if it's an infinite group. Um, and so basically, but so like we have this function, that projects any vector in the vector space onto the part of the vector space that is invariant to rho, like this representation of the group. And so basically, like, you can tell it, like, rho might just be zero. You can take this average and this average, and for example, for every irreducible representation, this average is just zero, because there is no part of the representation. The representation acts on the entire vector space. There's no part of it that is just kind of like chilling, not doing anything. But then in general, so like, so the phi maps onto the invariant subspace, and the trace of phi is the dimension of the invariant subspace. And since the trivial representation has dimension 1, that's actually just the number. If like, the trace of phi is like 3 or 4, then that means that there's there's 4 copies of the trivial representation just kind of chilling out, sitting in your representation. But and then, so this is actually something that I like realized I should put, like, because because rho, the original rho um is a representation. The whole thing is a representation. Then whatever, like, so if phi isn't 0, then the orthogonal complement of phi, like the space of and like the space of v that is 0 and doesn't have the trivial representation in it, that is also a representation. So whenever you do this, you are splitting the representation into two pieces, and one, in this case, one of those is like just all of the representations of the trivial all of the subspaces of the trivial representation. But then whatever you have left is also still a representation. But whatever is left, like if phi is 0, or like that doesn't imply that rho is irreducible. It might have, it might be the direct sum of two non-trivial representations. Does that make sense? I'm just going to say, does that make sense after every slide? But so notice, like, so this before, you're like, well, where's the trace? Like, why are you talking about characters? And this is where it really comes in, that the trace of this map is the dimension, is the the dimension of the like whatever the trivial subrepresentation, and it's and even more, it's the number of copies of this trivial subrepresentation. And it turns out that actually, in general, if we're looking for subrepresentations, we have this big representation and we think that we can break it up. This is just how we do it. And like previously, so previously we had this same thing, except we didn't have this like row triv of G, and it was just 1, and that's because that's what the trivial representation is. But in general, we can take two representations and just take this kind of, and it's what this is it's an inner product of functions. Almost. And it's like a dual, it's a dual function. It's like a map in the dual space. And that's why there's the conjugate transpose in there. But we can take this, like multiply these together, and this ends up being incredibly useful because, so we have this new map, so now the new phi is, is just like, we take two, we have two representations, and we're doing this kind of bottom thing where, and this is, down there, it's matrix multiplication. It's a sum of these matrix multiplications. But if we take the trace of this new map that is this like average sum of matrix multiplications, then because, then what we end up doing now, we have really properly turned it into an inner product. And, like because of the linearity of the trace, so it went from a matrix multiplication to, now the trace sends, rho of G to, it's a complex number, and, and the trace of rho of the conjugate or the conjugate transpose of tau of G, then this is an inner product. And it's got all of the lovely, inner product rules. And in particular, it's great because this tells us how many times tau appears as a subrepresentation of rho, or of rho in tau, because it's symmetric. And this ends up being really fucking cool. Does anyone need me to like kind of explain this, or like how it works?
Maybe this is a silly question, but you're saying that, like, I understand that this function is symmetric, but what would it mean that both rho is a subrep of tau and the other way around at the same time?
Okay, no, that's not a silly question, and so it's so basically, like, if there's a couple different I should have said that more clearly. So if rho has like if they have a different number of dimensions, then uh, if they have a different number of dimensions, then like then you can put them in any order. Like say that if tau has more dimensions than rho, then like if this inner product is like a positive number, then then rho is a subrepresentation of tau, and if they're well, wait, one sec. Let me think about this. Okay, I should be more clear. So if one of them is irreducible, like, okay, yeah. So if one of them is irreducible, then, and like if you know that, because the way that this comes up is oftentimes you have an irreducible representation and you have a representation where you are pretty sure it's not irreducible, or you're just not sure at all, but you're pretty sure it's not irreducible, and you want to check if the irreducible one is in there. Then so necessarily in that scenario, then they'll have different like a different number of dimensions, and also like you can't be a sub representation if you're bigger and you have more dimensions than the other one. If neither of them are irreducible, but and they share like some irreducible subrepresentations, then you will actually see like you'll get like a number where that's like kind of corresponds to how many irreducible representations they share. But if both of them are irreducible, as I think we're about to find out, it's either 1 or 0. It's either they're the same or they are not the same. And this is why like it's 0 if they're not the same, and it's 1 if they're the same. And in general, that's actually also how you tell whether or not that's how you tell whether or not a representation is irreducible, is that it's irreducible if and only if it's the inner product with itself is 1. Does that answer your question? That was kind of a lot.
I think so. Yeah, that's interesting. Thanks.
Yeah. But yeah, so you need to kind of be careful in terms of like what like the way that this goes is you need you're like, if you've got this new group and you've got a representation for it, then like you search as much as you can for n irreducible representation, and then you can kind of use that as like a probe to go and like pick apart any other representations that you have. Because if all you have are 2 reducible representations, then it's a lot trickier to it's just kind of trickier to figure things out. But so in this case, let's say that we know that tau is irreducible, and so like rho has more dimensions than tau, and what this means is that and so theoretically, like let's say we take this inner product and it's equal to 2, and again, if just one of these is irreducible, then this is always going to be a integer number as well. But so what this means is that there's a base, like literally for this full row, there is a basis where you just have 2 copies of tau just like hanging out, and then there is something left, this like row core that that is also still a representation, but is just smaller, like it's the full dimension of V minus 2, whatever the, 2 times whatever the dimension of tau is. And then this is kind of what, we do, is we're like, all right, like this is our tool, like if we have, just, a couple of one or two irreducible representations and then a really big representation, then just kind of bit by bit, we can break off the irreducible pieces, and then we're going to have something left. And this might and probably isn't irreducible, but, then we can kind of, go and like work on this smaller rho core. Does that also hopefully make sense? And then and then so we don't know that rho core is irreducible, but it's actually really easy to check, because then we just we've got rho core, and for any representation we can find we can check if it's irreducible by just taking the inner product with itself. And so here, I know that we mentioned this last time, but it is very important because, previously, like kind of when I said, like, okay, so if you just have a really big representation, then you can kind of break it apart and find like all the smaller irreducible ones. And actually, we always get a really big representation, and it's the permutation representation, or the regular representation. And that is, you have a vector space that is the size of, it has dimension equal to the order of the group. And so each basis vector is one element of the group. And the way that this works is like, so to do this, you do need to pick an order for, you need to pick an order to have your group elements in. But then once you do that, then it's all ones along the diagonal for the identity element, and then every other element, it's like how that element permutes the order. And so for this, it's it's also called a permutation representation, because this is a six-dimensional vector space. Like, this is not the symmetric group on 6 elements. That has 720 elements in it, right? Like 6 factorial. And so there's like 720 permutation matrices. This is just 6 of them. This is like, this representation is way too big. There are only 6 of these permutation matrices. And so, I don't know, can you like look at this and kind of like get how this acts on like the 6 elements of the group? And I would actually, I'm going to call attention to one thing. You will notice that the diagonals on this are all 0. And this is just a fact of the regular representation, that the character for it is, the trace is the, like 6 for the identity. It's all ones along the diagonal, and 0 for everything else. And that's because like they're, something else, I mentioned, but like if you think about how 3-2-1 acts on every other element of the group, if you translate the entire group by 3-2-1, it sends the identity to itself. But there's no element where it's like, there's no element that actually goes to itself when translated by 3-2-1, when acting on 3-2-1 by itself. 3-2-1 changes every single element of the group. Does that make sense? Do you like believe, is there anyone who doesn't believe that for this representation that is way too big, on the identity there are ones all along the diagonal, and there is all zeros on the diagonal for every other element. Okay, cool. I'm glad. So there are a number of cool things about the regular representation, but one of them is the fact that so the regular representation is the same as the group algebra and is the same as all functions on the group. And the way that you do this then is, and the group algebra is also a ring. But the way that you do this is like, so the function maps, it maps g to 2, and it maps, h to -3, and it maps I to, something else. And basically, for each of those elements, you get this big ass matrix. And what you do is you just add up those matrices weighted by, the value of f. And it turns out, and so this is like all sparse and whatever. And, but like this, you sum, if you sum a bunch of these up, it would end up being like kind of a big hairy matrix. But this acts precisely the same as a function on the group G. And yeah, so that's like f of g is just a scalar, and it's that's scalar multiplication times the matrix, regular row of G. And you get these matrices, and you can add them, and you can subtract them, and then you can also do convolution, which turns out to be, you can just do it by matrix multiplication, and it's great. But yeah, it's a 120-dimensional vector space, and there's 120 basis elements, and 120, or sorry, there not 120. There are it's a vector space that has the same order as the group, and it's just and that's I don't know. It's just very nice that you can all of these things are essentially the same or totally isomorphic. But so now, all right, this is we're getting to like kind of the big thing, and the regular representation is not irreducible. It's nowhere close, but from this process that we kind of built up before, we're like, all right, if I have a big representation, then I can break off bits of it. Actually ends up being very elegant when you think about the regular representation, because if I have some irreducible representation, then if I am doing this inner product, then so that first line I have is just the definition of the inner product, character of row times and I don't know, that's supposed to be row reg and row a rep and not tau, but you just kind of multiply the characters and sum it up. But what I drew your attention to and asked if you all believed, we can split this up where if we just just bring out the character for the identity and then just sum over all the rest of them, except for the regular representation, for everything that isn't the identity, the character is just 0. So this like right half of or this right sum just totally disappears, and then all we're left with is the character for the identity, but that is just ones along the diagonal. And so that is the, and so that's just the dimension. So does this make sense? And yeah, I'm sorry that it should, row reg and row rep, not rho and tau. But
And so what the last line means is that the representation, the dimension of your sub-representation must be prime factor, or maybe not quite prime factors, but they must divide the order of the group. So that's where the prime
yeah,
factors come in.
yeah, yeah, exactly. And so, well, and so even more. So every irreducible representation, and oh god, okay, I should have gotten this right. So the dim of the so this is like 1 over the order of G time the dim of the regular representation times the dim of whatever irrep you've got. But the dimension of the regular representation is the order of G. And so so for the inner product of the regular representation and the irrep is just the dimension of the irrep. And that means that every single irreducible representation appears in the regular representation with multiplicity equal to its dimension. So if you have a 3-dimensional irrep, then it appears in the regular representation 3 times. And so this one means, okay, cool, there are only finitely many irreps, which is great. It would be very difficult if there were infinitely many. But more than that, so the dimensions of the irreps, if you sum, the dimensions squared have to be equal to G. Have to be equal to the order of G. And this is actually another really important tool where if you don't even know like what the irreps are necessarily, like if you've got like 2, you can kind of be like, all right, how many, like what are the possible remaining dimensions? You can kind of play Tetris, and be like, all right, like I was literally just doing this with a group of order 20, and I'm like, all right, I have 1 4-dimensional irrep and 2 and 2 2 1-dimensional irreps. I'm like, all right, so that's 16 plus 2 is 18. And I'm like, all right, I guess there must be 2 more 2-dimensional irreps because, you can't, like, I had 2 left and there's no way, like, there, it had to, like, I can't have a dimension square root of 2. And, it's, but then, because, and this I maybe have not justified sufficiently well, but so for each, so the dimension of the space of all functions on G is the order of G. There are d squared, so like, and if for each row, like there's like d row squared, like matrix elements of the representation, and it turns out that the matrix entries, and so that's the same. Like the number of matrix entries is the same as the number of elements in the group is the number of dimensions in the space of all functions on the group, and so all of the matrix entries of the irreps provide an orthonormal basis for the space of all the functions on the group. And you can kind of think like, and if that's like a little weird and a little too like not very concrete, so like I talked before, like every function on the group can be represented as like this weighted average of these really huge matrices, of like, the order of the group times the order of the group. But it turns out that really is too wasteful. Like it's too big. And you can actually just have the and so you can actually have like a basis for every function where instead of like showing up 10 times, each irrep shows up once, and you get this block diagonal, essentially Jordan form for all of the functions on your group. And that's it. That's the Fourier transform. Like that is, like we were just kind of looking for representations, and then it turns out that there is this wonderfully nice way to do it, and you get these block diagonal matrices that represent, they're super sparse, and you perfectly represent every function on your group. And yeah, and it's beautiful. You can compute this Fourier transform, and it's just like, and it's, so you get this function f hat, and it takes in an irreducible representation. So, so the values it takes in are it takes in an irreducible representation, which basically works as, like in the Fourier transform, it works analogously to in the Fourier transform that you're like familiar with, is it works analogously to a frequency is like each a rep, and then so you end up getting this like weighted sum of matrices, and it's it's unitary, like it preserves the norm of your function, preserves like the inner products, and you lose no information. It's totally reversible. And so like if you just have f hat, then you can get the original function back by taking the character and summing it. And it's, I guess also, if you have f hat, because it's an orthonormal basis, then that's part of like why like this ends up being really nice, is it's very like if you have this Fourier representation, like it's really fast to compute the inner product in the Fourier basis, and then something that I can't believe I don't have a slide for, but like that convolution is just matrix multiplication in the Fourier basis, and it's just really beautiful. And so this is actually all I have, because and like there's a lot more to talk about, and I like kind of motivating like why for abelian groups this is the same as like the Fourier transform that you know about, but I was like putting this together, and yeah, we're already, it's almost been an hour, though I guess we started a little late. But I just kind of wanted to like really like kind of bring you through like the like the finding the irreducible representations, and then being like, wait, this is easy. And I don't know. So this is all I got. But any questions?
Thank you very much. At least I really enjoyed it. I think your explanations definitely connected some dots for me. So
Yeah.
I'm happy about it. Like I think I asked you about, but in DMs about like connection with graphs and graph homomorphism, and the more I see this, the more I feel there's got to be a connection. So
there definitely really has to be, and I guess I would be curious in particular with graphs, like looking at the automorphism group of a graph, and and stuff like that. And
there's definitely stuff like that, but there's also, even for graphs, we have a notion of a graph Laplacian that's like the Laplacian operator before graphs. And if you take it's a symmetric matrix, and you can take the eigendecomposition, and you have an orthonormal basis of eigenvectors that also work like the Fourier transform before the nodes of your graph, for the space of functions on the node of your graph. So, and I had been thinking about that like more than a year ago now, about how if you look at these eigenvectors, they basically tell you about the automorphism group of your graphs. But that's something I never pushed too far. But yeah, really.
Yeah.
Yeah.
I mean, I guess the thing that I like, and again, part of why I kind of wanted to motivate, like really being like get you to think about, or trying to get you to think about irreps and is that like what I think is the core of this is this idea of so in this kind of general case where the group isn't abelian, there are not all of the necessarily the nice properties. Like when you have an abelian group, the characters are actually a group themselves, and that's like a kind of a big part of like basically like if you have an abelian group, then the characters are a map to the circle, and so like you multiply it enough times, and eventually it comes back. This is actually maybe Hawk what you were talking about, and but like but you don't get that for a non-abelian group. The characters don't necessarily form a group themselves. But the core of it is this idea that you have this kind of dual space that has all of the information in your group, and this is also like how like I have been reading a lot about Tanaka Krein duality, and actually I think maybe we should talk some uh, about graphs and stuff, because the thing that I have been kind of like where I would like to take this is looking at finite automata, and like you can represent an automata with a a deterministic automata with like a directed acyclic graph on like the states of the automata and the transitions and stuff, and I know that there are like looking at the Laplacian of that is going to be relevant, but just that there's this idea of like, oh, there is this totally other space that is precisely the same in all of these important ways that we care about, and we can move back and forth smoothly, and so that we can like and when I look in this dual basis where it is structured on these irreducible representations, then all sorts of things are just become really clear. So something that I've realized in my the research project in grokking that I've done is and I think this is maybe like too basic to ever like put in a textbook, except maybe as an exercise, but or maybe it's just not quite true in general. But something that I've noticed or realized is that if you're looking at if you have a function that is just like a one one on a subgroup of the group and then zero everywhere else, and then you take the Fourier transform of that function that is just like the like what is the indicator function for a subgroup, that will have non-zero values on only one irrep. And it'll be the irrep that where if you restrict the representation to that subgroup, it's got the trivial representation as like a subrepresentation. But you have this idea where I don't know, like if you're just looking at a function, and you don't know that what it's doing is picking out this one subgroup, like it can be kind of not obvious like what's happening, but looking at irreducible representations, when you like it's basically like you take the Fourier transform of a kind of a normal signal or whatever, and you're like, oh, all of this signal is focused on this one frequency, and it's just this lens that you can use that's just it's very powerful, that a lot of really important information is all kind of wrapped up in you can in this other way to look at your function.
So like I honestly I don't understand it well enough to come up with really good questions, but I mean I have lots of questions and just have very coherent questions.
That's fine. That's fine.
It's one thing I was wondering if you could sort of help clear up a bit is the machinery that you use to develop the matrices themselves, they were all permutation matrices. So by
Mhm.
definition, they're all sparse in the sense they all have the one element in each row or column. So
Sure.
that in and of itself, that by their nature would lead to having the middle equation there on the second element on the right side becomes 0, of course,
Yeah.
because there's only one matrix that has the ones in that diagonal. Everything else is going to be 0 diagonal.
Mhm.
So isn't that the very property of permutation matrices?
So this is, so not quite. So
Okay.
in a general permutation matrix, so if instead of like the regular representation of S3, so um so this is so if instead of the regular representation of S3, this was just S6, then there would very well may be like, and so in that case, like instead of permuting the permutations of 3 elements, we're just permuting like the elements of a 6-element array, then you could have a permutation of that leaves the last 3 elements in place, that like is only, like a subgroup of S6 is S3, and you only permute the first 3 elements.
Okay.
And so in that case, then like as a representation of S6, like that element, or those elements that leave the last 3 the last 3 like numbers fixed, will have just ones along the diagonal in that permutation representation, or that like for the symmetric group, that's called the standard representation. And so this is a specific um, this is a specific fact of the regular representation. And actually, I should say that this representation of permutations of like, so like permutations of like the order of the group, this is how you prove that, oh my God, what is it called? But the theorem, it's someone's famous theorem, but the theorem that every group is a subgroup of some symmetric group, this is how you prove it, by embedding it in the permutation group with the number of elements as there are elements in the group. Does that make sense at all? But
To a
so,
large degree, yes. I mean, it makes more sense, but obviously I need to do
okay.
my reading further. But it's super interesting, particularly with the duality and the whole concept of how that moving back and forth. I mean, it just feels there's something really deep there.
It's really cool. And so yeah, so I think, and we should talk about, maybe not next week, maybe give, like, or I don't know, like we should maybe talk about like whether people like this kind of like switching from week to week. But there's like one, so I guess maybe like I think a good capstone to our like representation theory foray would be looking at the next chapter of the Diaconus book, where you're looking at random walks on groups, and it's, you can like, and Markov chains on groups, and you can use the Fourier transform to like prove really cool things about Markov chains on groups. And in particular, he proves that like, it only takes 7 riffle shuffles to get basically a perfectly shuffled deck of cards, which is like very cool. And but yeah, I think like, the now that we have this set up, that I think we can kind of talk about like, all right, how does this look for abelian groups? Because when I realized that I wanted to cut like talking about abelian groups and like all of that stuff, it was also like, I did have a slide on conjugacy classes, and the reason that like, but the way this goes is, the reason that the Fourier transform on abelian groups is so nice, and the one that we like, and that's like the Fourier transform that we know, is because it turns out that, so I have this thing where So the sum of the square dimensions of the irreps is equal to the group. Then you might be asking, like, all right, I know that there are finitely many irreps, but it turns out that there are the same number of irreps as there are conjugacy classes on the group. And for an abelian group, every element is its own conjugacy class. And that means that every irrep is one-dimensional, because, so there has to be one irrep per element squared is equal to the number of elements. And so there are no matrix irreps for abelian groups. You just get, elements of C, one-dimensional elements of C, one-dimensional scalars. And so your Fourier transform matrix is a diagonal complex matrix. And that's but explaining all of this, as well as really getting into conjugacy classes and then proving that the number of irreps is the number of conjugacy classes, I was like, this is too much. Though maybe also people don't care and will just believe me, and maybe I don't actually need to prove that for you. But anyway, so I think you're right. There is this really cool stuff, and I think we just kind of need to dig a little bit deeper to get there.
Yeah, I guess my intuition for abelian group is that because the representation elements have to commute, that means they must have the same eigenvectors.
Oh, interesting.
So you have all the matrices that have the same eigenvectors, and so only the eigenvalues must differ between the representation of your elements.
Oh, yeah, that might be cleaner. Let's talk about this some, because I was actually fretting about this last night. I was like, oh my god, can I do I need to prove for everyone, because I also I was kind of unsatisfied with the presentation of this class, this thing about the conjugacy classes and whatever. But maybe we don't need to talk about the conjugacy classes. Maybe that would be a lot cleaner. But anyway, yeah, that's cool.
Yeah, maybe I think we can do that, but later in the chat.
Yeah.
It's getting late for
a
non-zero amount of people, so.
Yeah, well, thanks so much. And yeah, if people have any other questions, and just hit me up in the chat. And yeah, this was a lot of fun.
Yeah, before we end,
take care.
Yeah, first of all, unless anyone else has questions about your representation theory, so first of all, thank you very much for the presentation and discussion. I really enjoyed it. We do still have something to discuss about next week. So either we do another thing on representation theory, or I guess the most obvious second or first candidate would be something on so multilinear algebra and tensors, which a few people have requested, and there's been some amount of enthusiasm, and I think it would be worth it. So
yeah,
I don't know if people here have any particular preference between representation theory 3 or multilinear algebra and tensors.
I can go either way. I mean, I don't know if you had any specific concrete ideas about kind of how to extend the kernel NTK stuff, but of those three, I would be down for any of them.
Yeah, I think for the NTK, it will have to wait until I read more papers on that.
Okay, yeah.
Especially if I try to read the tensor programs papers. Yeah, so it's sort of why I think maybe moving first into basic multilinear algebra, because it should be easy to cover and very useful either way. So
yeah,
because I think the nice thing is that it's useful even on its own. It's useful for representation theory. It's useful if we move on to geometric deep learning, because if we talk about manifolds, we have to talk about tensors and so on. So I think it's overall a very easy thing to do, and worth it in general for many things.
Yeah, I'd definitely be down for.
Also, thanks Hawk for finding an excellent source for that one. So
yeah.
Does anyone have a particular preference, or can we just choose?
Seems like multilinear algebra might be helpful just as like a prereq before we go into other things. But I'm really fine with anything. And thank you for the talk this week.
Well, yeah, I think let's go with multilinear algebra. I think that'll be good. And,
Okay. Yeah, okay, then I think I can handle that without any problem. So I'll send exactly what you should read, but basically it's this one source, and it's 100 pages, but I think if we brush up on like the basic vector covector and then move on directly to tensors, that should be already a nice thing.
yeah, sounds great. All right, I need to run, but thanks everyone. This has been lovely, and yeah, y'all are a great audience.
Thanks for the presentation. Can we can I just put in my one quick request? Can we actually have a wrap up on this? One later part. It feels like there's like we're
Oh yeah,
almost
Yeah,
where it comes
definitely
from
that'll be.
here. We can make it more concrete.
yeah. Let's shoot for then. The week after next, let's do one final representation theory, and I'll like, and it'll just be about the Fourier transform, and I'll do, um, something. Yeah, I think probably something from Diaconus, and like, like proving bounds on, the number of riffle shuffles it takes to perfectly shuffle a, or very close to perfectly shuffle
Even
a,
then, I thought the example in Kondo's thesis about doing statistics on group valued data
Mhm.
was very interesting as well.
Yeah, no, it's really cool, and again, it's been useful like in my project. I mean, and it's actually interesting where like in my project I'm now like, like I don't think that the representation like, I don't know, it was between the six of us, but there was like a recent paper where they're like, the this neural network learns representation theory, and I actually don't think that's true anymore, but the representation theory is still like key in being able to analyze it and actually figure out precisely what it is doing, which is this like double coset circuit, which is very cool. But anyway, um yeah, so yeah, but yeah, we will definitely do one more on this.
Okay, then I think then we can wrap up for the day. So thanks everyone for coming, and see you guys next week.
Yeah, all right, see you.